So now we're going to get more specifically into alkenes. And the way we approach this chapter is the way that we will do most things in this course going forward. And that's that we talk about some of the properties of the functional group. If there are properties that are relevant or important, we'll probably do some nomenclature, although there's a couple functional groups later on in the course that we kind of skip the nomenclature of. And then we look at reactions of the functional group. And in some cases, those will be reactions that make the functional group. And in other cases, that'll be reactions that the functional group can do. So with alkenes, which are, of course, our carbon-carbon double bond, we'll start with important properties. And probably the first and most important thing that we're going to start with is what differentiates them from alkanes. So alkanes, we've said, are pretty boring. We talked about a total of 2 reactions of alkanes. Why was that? Well, with alkanes, they just don't do much. But as we start talking about alkenes, we're going to talk about close to a dozen different reactions of alkenes. So just that small difference of having a carbon-carbon double bond, turns out it makes a huge difference in reactivity. And it's all because of the pi bond. Because that pi bond is present, we don't have any free rotation in alkenes. In other words, once you've formed an alkene, it's locked into the conformation it forms in. And so this has a lot of consequences. Starting here. So if I drew these 2 molecules, are these the same molecules or are they different molecules? So we would say that these are conformational isomers of butane. In fact, we covered this when we were talking about Newman projections. To get from one structure to the other, all we have to do is rotate about this carbon-carbon double bond. But with alkenes, the story's quite different. Are these the same molecule? The answer is no. These are isomers. Why is that? Again, because we cannot rotate about this pi bond. And so these 2 molecules are locked into these conformations. The only way that you can interconvert these is to actually break the pi bond. How different are they? Well, for one, if we tried to measure the melting point of each of these compounds, the compound on the left has a melting point of 105 degrees, and on the right, 139 degrees. So, very, very different melting points. And other properties about them will be different as well. Later on, we'll talk about which one's more stable, as well as which one's more reactive. So in addition to learning how to name alkenes themselves, we also need nomenclature that describes each of these isomers. Now, if the alkene is nice and simple like this one and has only one substituent on each carbon, there's one name we can use, but in most situations, there's actually a different set of nomenclature that we'll use. So here, where the two groups coming off the alkene are on opposite sides, this alkene can be referred to as trans. Over here, where the two groups are on the same side of the alkene, pointing in the same direction, we call this cis. Now, if you had a cis and trans alkene, is that something that we can easily determine which is which? And I don't mean from looking at the structure. What I mean is from, if we actually had the compound in hand. So you may recall back in the NMR chapter, we talked about this thing called a coupling constant. And we said it was the distance between the peaks in a splitting pattern. I think I also said that day that we would come back and revisit this idea of coupling constants when we got to alkenes. And so it turns out that the coupling constant easily lets you distinguish between a cis alkene and a trans alkene. How does it do that? Well, if the alkene is trans, then the coupling constant, or the distance between the peaks in that splitting pattern, will be between 12 and 20 hertz. Whereas for a cis alkene, the coupling constant is much smaller, 6 to 12 hertz. And so that's how we can distinguish between them. But the only problem with cis and trans for nomenclature is it only works well for when we have an alkene that has one substituent on each side. For an alkene like this one that has 4 different substituents, cis and trans don't really apply. And so I'm actually going to save all of the nomenclature for the next video, but that's where we'll pick up, is what do we do in a situation like this? How do we name this? And how do we name it so that it can be distinguished from its isomer, a compound that looks like this?